Welcome back to the lecture series of vector calculus. So in the previous lecture actually we have discussed what do you mean by the scalar function, what do you mean by the vector function, and how we can define a curve and a surface whenever we are considering a vector valued function. So in this lecture I am going to discuss what is the point function, what is the scalar point function, what is the vector point function, and what is the scalar field and vector field and related examples. So what do you mean by the point function? So point function means actually, say we are considering a three-dimensional plane or two-dimensional plane. Then there are different points. So if we define some function through which we assign some values, the values may be scalar, may be vector, but we assign some values to each of the points in that plane or in some region or in some domain or in some subset of that plane. Then this is called as the point function. So that means, what do you mean by the point function? So a function is there, we know that through function we assign some value or we actually get some output of value. So if we can take the different points in that plane, then corresponding to that point, if we assign some values, then actually this is the functional value. So since we are assigning some values in a particular point in that particular domain or the overall plane, so that is called as the point function. So as I have told earlier, the point function can be of two types, that is scalar point function and vector point function. So what is the scalar point function? Scalar point function means whenever we are assigning some real values or scalar values to each of the points in that particular region or in that particular space, that is called as the scalar point function. So scalar point function is usually denoted by phi xyz. That means in three dimension there are three variables x, y, z. So if we identify any point in that three-dimensional plane, so there must have three components, x, y, z component. So we are assigning some function phi to each of the components which is dependent on the values of x, y, and z. So this kind of function is called as the scalar point function. So what are the examples of scalar point function? So for example, we are considering the temperature distribution within some body at a particular point in time. That means we have taken a body. So we know that temperature is nothing but a scalar value. Then we are identifying or we are defining a function which actually identifies the temperature at a particular point in a specific time. So we can actually relate the temperature of that body at each and every point or at any point in that domain by some value. So say for example, I am defining the function. I am getting the temperature of that body at each and every point or at any point that is defined by x square yz. Say phi of u equals to x square yz. That means if I take a point x equals to 1, 2 and 3. So at 1, 2 and 3 the temperature will be x square into yz, that means 1 square. So 1, 2, 1 I have taken the point, so 1 square into 2 into 1. So that means 2. So temperature will be 2 units. That means by virtue of those points values, so by virtue of the coordinates of those points actually, we are identifying the temperature at each and every point of that body. So this kind of thing is called as the scalar point function. That means I am identifying some values or I am assigning some values to each and every point which is a scalar value. So another example can be density distribution within some fluid at a particular point. So density, we are taking a particular fluid, then at each and every point we are assigning some function that is dependent on, if I consider in three variable, that is dependent on say x, y, z. So by so we know that density is a scalar value. So by varying the value of that point or varying some values of x, y, z, we are defining a function that actually identifies the density at a particular point in that fluid. So at a particular point means just we need to substitute the value of x, y, z, that means the coordinates of this point. So by substituting the coordinates actually we can identify the functional value corresponding to that point that actually identifies the density. So this kind of functions are called as the scalar point function. Then we will define the vector point function. What do you mean by the vector point function? So similarly, if I consider any two-dimensional or three-dimensional plane or any body, then by changing or we assigning some function which actually indicates or provides some vector value to each and every point in that particular plane or in that particular domain, it is called as the vector valued function or vector point function, because through the vector we are actually identifying the value, a vector valued thing or vector value corresponding to each and every point in that particular body. So it can be defined as So since it is a vector valued function, so the function must have three components if we consider the domain or the plane in three-dimensional figure or three-dimensional plane. Then we assign some values to each and every point which is dependent on the coordinate of this point, that is xyz. So by changing the value of xyz, actually we can identify the vector value that is assigned to that particular point. So to the examples, the gravitational field of the earth. Say for example, I am defining, you know that gravitational field or gravitational vector, gravitation is a directional vector, or is some value that is directed towards the downward direction. So for example, if we assign some function, it's a gmm by r square, you know this is actually the gravitational force. So if I consider any point in the three-dimensional surface or in R, then I can assign some vector valued function. By putting the values of x, y, z on that function, actually I can identify the value of the gravitational field in that particular point. So since you know that gravitational field is nothing but a vector field or vector valued function, so that's why it is considered to be as vector point function, because by virtue of that function we are identifying the particular value corresponding to a point in that domain or in that plane. Electric field about a current carrying wire. So if I consider a wire, then at any point of that wire we can defining a function that actually identifies the electric field at that particular point. So that is also a vector point function. Similarly, we know that magnetic field is also a vector valued quantity. So if I consider a magnet, that each and every point of that magnet, I can identify the magnetic value or magnetic value by defining some function. So if I put the coordinates of that point in that function, then I can identify actually the magnetic field at that point of that particular magnet. So these are all examples. Similarly, the velocity at different points within a moving fluid. Say I have considered a fluid in three dimensions. So each and every point I can identify the velocity. You know that velocity is a vector quantity. So at each and every point, if I put the coordinate of that point, then by defining a function and putting those coordinates value, I can identify the velocity at that particular point. So all these things is the vector valued quantity. So if I can define a function at a that indicates the value of that particular things in a particular point of a field or of a space or of a region, then this actually called as the vector point function. Similarly, acceleration at different points within a moving fluid. Similarly, you know that acceleration is nothing but a vector valued quantity. So if I want to identify the acceleration at each and every point inside a fluid or in a fluid, then by virtue of a function that is nothing but a vector valued function that actually assigns some value at each and every point, you would identify this quantity. Then there comes scalar field. So whenever we are considering the scalar point function, so this function actually assigns some value corresponding to a particular point in a domain. Now if I consider the collection of all such functions that could be defined in a region, that is called as the scalar field. Is that clear? That means what is the scalar field? The scalar point function that we are defining corresponding to a particular point, and if we consider the summation of all such scalar point values of scalar point function in a particular domain or region, that is called as the scalar field. So scalar field can be dependent on time or it can be independent of time. If it is dependent on time, then it is called as the if it is independent of time, then it is called as a stationary or steady state scalar field. That means this is not dependent on time. So if it varies with time, if it is dependent on time, then the scalar field is defined as phi xyz t. So actually by varying the value of t, actually we can identify the scalar field as the scalar point function by changing the time. At a particular instant of time, I am coming to this coordinate, then I am getting a particular value. If I change the time and come back to that point, then I can get the different value. So this is actually the time dependent scalar field. So I am giving one example. Say for example, so this is the equation of a three-dimensional surface. This is the x-axis, this is the y-axis, this is the z-axis. So whenever I will study how to draw this surfaces in MATLAB or Mathematica, then you can draw this curve. So generally we are considering a surface. So if I consider any point, so I have defined a function. So the equation of this is dependent on x, y, z. So if I take a point, then I will get a value of that surface at that particular point by putting the coordinates. So this is actually some value that we can identify from that function that actually represents the surface. Similarly, if I consider this point, then if I know the definition of the function, then if I substitute the coordinates there, I will get the value at that particular point. So in that way, I can get the functional value of that particular. This is a scalar valued function because this is a scalar field, because no vector or no directions are there. Directions are mentioned here. So if I consider any point, then if I put the coordinates of this point in that function which is defined, or through which the surface is defined, then I could identify the value at that point of the surface. Similarly, what is the vector field? So vector field means if I consider a vector point function defined over a region, it's called as a vector field. That means whenever I am identifying a vector point function, so vector point function is some vector value that is assigned corresponding to each and every point in a particular region. So if I consider all such vector point functions in a region, that is called as the vector field. Similarly, here also if it is time independent, that is called as the stationary or steady state vector field. Otherwise, the vector field that can be represented in the form of this. That means this is a vector point function that is changing with respect to xyz. So if I consider all such vector point function in a particular domain or region, that is called as a vector field. So here I am consider the wind speed at each and every point in the surface of Earth. So actually, so if I want to identify any point in the surface or in Earth surface, so latitude and longitude is required. Similarly, I can vary height. So here I have fixed actually the height. So this is observed at 34,000 feet height. So at that feet, I am identifying or I am defining actually a vector point function that actually identifies the speed as well as the direction of the wind at a particular point. That means I am varying the value of xy, that means the latitude and longitude. If I vary the value of xyz, so xyz is actually nothing but the coordinate of any point in the space. So at that point, by defining that function, I could identify actually this is the value of the vector field that identifies the wind speed. So at this point, this is the actual wind speed, value of the wind speed. I will get the magnitude by putting the values of xyz at that defined function, and I will get the direction of at that point of the wind. So I am getting the direction of wind. So here I am getting the quantity of the wind speed at a particular point by defining the value of xyz in that function. As well as since this is a vector valued function, so I am getting the directions also corresponding to each and every point, and thus I can identify the wind speed. So these are all examples of the vector field or vector point function. So in this lecture I have discussed what is the point function, what is the scalar point function, what is the vector point function, and what is the scalar field and vector field. So stay tuned for the next lectures, that are the gradient, divergence, curl, and what is the directional derivative. So all of these things you will study in the next lecture. So stay tuned till then. Thank you all for watching this.